30,000 stars are moving the wrong way through the Milky Way. They do not follow the broad traffic of our galaxy like the Sun and most of its neighbours do. They drift, like survivors of some much older story, as though part of the Milky Way does not belong to the Milky Way at all. That alone would be strange enough. But what makes it stranger is how little confidence we still have in the overall structure of the galaxy these stars now inhabit. We live inside the Milky Way, surrounded by its light, and yet some of its most basic features remain frustratingly uncertain. So how did our own galaxy stay this mysterious for so long? I'm Christopher Vale, and you're watching Sleepy Explorer. Join me today as we take a closer look at the galaxy we call home. Together, we're going to follow the long path from confusion to clarity and see why understanding a galaxy becomes far harder when you are trapped inside it. It is easy to assume that by now the Milky Way should be one of the best understood objects in astronomy. After all, it is not some faint smudge at the edge of the observable universe. It is our home system on the grandest scale available to us. The vast stellar city that contains the Sun, the planets, and every naked eye star you have ever seen. For centuries, human beings have looked up into that pale river of light across the night sky and known, at least in broad terms, that they were seeing the disk of a galaxy from within. But broad terms are not the same as real knowledge. Once you move beyond the comforting familiarity of that glowing band, the confidence begins to fall away. Even the simplest questions become strangely unstable. How many stars are actually in the Milky Way? The answer is not precise. Estimates have ranged from roughly 100 billion to perhaps 400 billion, depending on which assumptions are built into the calculation and how much hidden mass and faint light one allows for. That is not a small disagreement. It is the difference between having a rough census of a city and not even knowing whether its population is 2 or 4 times larger than expected. The same uncertainty extends to the shape of the galaxy itself. You might imagine that the Milky Way's spiral pattern was settled long ago, neatly pinned down in textbooks and museum graphics. But for years, astronomers have gone back and forth over a surprisingly basic issue. Does the Milky Way have 2 major spiral arms, or 4? The current picture leans toward 4, but the fact that the question remains so unsettled for so long tells you something important. The problem was never a lack of intelligence, it was perspective. There is a simple analogy that captures the difficulty better than almost any equation. It is easier to stand at a window and study the shape of the house across the street than it is to understand the structure of your own house while standing in one of its bedrooms. From outside, the walls, roofline, and proportions all reveal themselves at once. From inside, you are surrounded by pieces. A hallway here, a corner there, a glimpse of one wall, the sound of another room beyond it. You can infer the larger plan, but you do not see it directly. The Milky Way confronts us with the same problem, only on a scale so enormous that ordinary intuition breaks down. When we look outward through the galaxy, we are not peering through empty space. We are looking through a cluttered and luminous interior, filled with stars, gas clouds, dust lanes, and bright regions of star formation. Everything that helps make the Milky Way beautiful also helps make it difficult to read. Light from distant stars can be dimmed, reddened, scattered, or blocked altogether. Entire regions become crowded with overlapping sources. Shapes that would be obvious from far away dissolve into confusion when viewed edge-on from within the disk. This becomes worst in the direction of the galactic centre, where matter is most densely concentrated. There, visible light struggles to penetrate the tangled interior of the Milky Way. Astronomers sometimes describe parts of this region as a zone of avoidance, not because nothing is there, but because ordinary observations become so obstructed that the structure beyond is hidden from easy view. In practical terms, that means one of the most important regions of our own galaxy has often been one of the hardest to interpret. We have lived inside the Milky Way while staring at its brightest depths through a veil. That alone would be enough to make the galaxy difficult to map, but there is another problem layered beneath it. Seeing a star is not the same as knowing where it is. A dim point of light on the sky could be a small nearby star or an immense distant one. Two stars that appear close together may, in fact, be separated by enormous distances along our line of sight. If you want to build a true picture of the Milky Way, not just a flat star chart but a real three-dimensional structure, you need distances. And distance in astronomy has always been one of the hardest things to measure well. This is where the story begins to deepen. The Milky Way did not only confuse us because we were inside it, it confused us because for much of human history, we lacked a reliable sense of depth inside it. We could see the galaxy as a glowing band, but we could not easily tell how that band was layered, how far its stars stretched, or which features belonged together in space, rather than merely overlapping by chance from our perspective on Earth. A galaxy seen without depth is like a city at night, viewed from far away through fog. The lights are there, but the streets between them remain uncertain. Some stars make this task a little easier. There are classes of stars whose intrinsic brightness can be inferred from the way they vary over time, which allows astronomers to compare how bright they appear with how bright they truly are, and estimate how far away they must be. These stars became some of the stepping stones by which cosmic distances were first measured, but the Milky Way contains far more stars that do not politely announce their true luminosity. For them, the geometry has to be reconstructed another way. And that is why the Milky Way remained vulnerable to misunderstanding long after galaxies were recognized as real systems of stars. We were not simply missing data, we were missing the kind of data that can turn a sky into a structure. Without that, arguments about spiral arms or stellar populations were not just academic quibbles, they were symptoms of a deeper limitation. We could describe the galaxy's appearance, but not yet read its architecture with confidence. There is something humbling in that. Human beings learn to calculate eclipses, predict planetary motion, and eventually send spacecraft beyond the solar system, yet our own galaxy still resisted clean description. We could catalogue galaxies millions of light years away as spirals, barred spirals, ellipticals, and irregulars, sometimes with a confidence that sounded almost casual. Yet the Milky Way, the one galaxy we inhabit, kept slipping away whenever we tried to reduce it to a simple diagram. Familiarity in this case did not make knowledge easier, it made it harder. The irony becomes sharper when you consider how galaxies are often presented in popular imagination. They appear as majestic pinwheels or glowing ellipses suspended in blackness, cleanly isolated and easy to admire. But those images are usually images of other galaxies, external views that we can never take of our own. No spacecraft has travelled far enough away to photograph the Milky Way from outside. Every image you have seen of our galaxy in its entirety is, in one way or another, a reconstruction. Some are informed and sophisticated reconstructions, some are built from excellent data, but they remain acts of inference, not direct portraits. That matters because inference can be transformed by new information. A small improvement in how we measure stars can force a much larger improvement in how we imagine the galaxy as a whole. This is exactly what has happened in recent years. The Milky Way has started to sharpen, not because the galaxy itself changed, but because our way of reading it changed. Suddenly, the blurred and crowded interior began to develop depth. Motion stopped being a nuisance and became a clue. The sky, observed patiently over time, started to reveal which stars were local, which were distant, and which were carrying the memory of ancient collisions. That last point is one of the most striking. Once astronomers began to follow stellar motion with enough precision, some stars stood out immediately. They were moving in the wrong direction compared with the main flow of the galaxy. They were not merely eccentric. They seemed like immigrants from another system, relics of smaller galaxies that had once fallen into the Milky Way and been torn apart. In other words, one of the reasons we misunderstood galaxies for so long is that galaxies themselves are not quiet, finished structures. They are historical objects. They carry scars. So the deeper question is no longer just why the Milky Way was hard to map. It is why we expected simplicity from something that was never simple in the first place. A galaxy is not a frozen pattern of stars. It is a living record of motion, collision, birth, erosion, and time. It is a structure we inhabit, and a history we are still trying to decode. From that perspective, the uncertainty begins to feel less embarrassing and more inevitable. We were asking a dynamic thing to present itself as a static picture. Still, inevitability is not the same as defeat. Astronomy has a long habit of solving impossible-looking problems by changing the scale of observation. If you cannot move far enough away to see the Milky Way from outside, then you must find another way to create distance without leaving home. You must turn motion into geometry. You must use time as part of the instrument. You must let the orbit of Earth, and eventually the motion of the solar system itself, become part of the measuring process. That is where the modern story truly begins. The mystery of the Milky Way did not start to yield because we suddenly found a perfect place from which to observe it. It yielded because astronomers learned how to measure tiny changes in position with extraordinary precision, and to do so over years rather than moments. What looked at first like a fixed sky became a moving field, and once those movements could be tracked, the galaxy began to unfold in depth, which leads to the deceptively simple question that changed everything. If you cannot step outside the Milky Way to see its shape, how do you measure the distance to the stars that make that shape in the first place? You do it with parallax. It is one of those rare scientific ideas that feels almost childishly simple the moment you see it. Hold up a finger in front of your face and close one eye, then the other. Your finger seems to jump against the background, even though it has not moved at all. That shift is not an illusion in the ordinary sense. It is geometry revealing itself. The closer an object is, the more its apparent position changes when your point of view changes. If you know the size of that change, and you know how far apart your two viewpoints are, simple trigonometry can tell you the distance. That is easy enough when the object is a finger. It is still manageable when the object is a tree across a field. But stars are another matter entirely. They are so far away that the shift in position is vanishingly small, almost absurdly so. The effect is still there, but it shrinks with distance until it becomes buried in the limits of your instruments. That is why distance has always been one of astronomy's great bottlenecks. The sky gives you light for free. Depth has to be extracted. The clever solution was to widen the baseline. Instead of using the few centimetres between your eyes, you use the diameter of Earth's orbit around the Sun. Observe a star, wait half a year for Earth to move to the opposite side of its orbit, then observe it again. From that much larger separation, nearby stars shift very slightly against the deeper background. The movement is tiny, but it is enough. In principle, that gives you one of the most direct distance measurements available in astronomy. In practice, of course, nothing is ever quite so clean. Stars are not pinned motionless to a cosmic wall, they are moving too. Earth is moving, the solar system is moving. The galaxy itself is a vast pattern of motion, so the astronomer's task is not simply to detect a little shift and declare victory. It is to disentangle several overlapping motions at once and decide which part comes from our own changing viewpoint, which part belongs to the star, and which part belongs to the larger dance of the galaxy around it. That is where time becomes so powerful. The longer you watch, the more the hidden structure begins to separate itself. A star observed once is a point of light. A star observed repeatedly over years becomes a track, or at least the beginning of one. The looping signature caused by Earth's orbit can be teased apart from the star's slower drift across the sky. Astronomers call that drift proper motion. And proper motion matters because, broadly speaking, nearby stars tend to reveal their motion more strongly than more distant ones do. This is the principle Gaia turned into an instrument of extraordinary precision. Launched in late 2013 and operating from the Sun-Earth second Lagrange point, Gaia was designed not just to look at stars, but to return to them again and again and again. It did not build a picture of the Milky Way from a single grand exposure. It built that picture the patient way, through repetition. Across more than a decade of science observations, Gaia accumulated over 3 trillion measurements of more than 2 billion objects, turning the night sky from a static map into a dynamic dataset. That scale is difficult to feel at first. 2 billion stars still represent only a fraction of the stars thought to inhabit the Milky Way. But it is the quality of the sample, and the precision of the measurements that changed everything. Gaia was not merely collecting points of light. It was measuring positions, distances, motions, brightnesses, and physical properties with a consistency no previous mission could match. Instead of asking where stars appear to be, astronomers could ask where they are, how they move, how bright they truly are, and how they relate to one another as members of a single galactic system. The spacecraft itself was built for exactly that purpose. Gaia used 2 telescopes looking in different directions, whose light was brought onto a single focal plane with a camera of about 1 billion pixels. That design allowed it to compare angles with extraordinary stability. Alongside this astrometric work, Gaia also carried instruments able to measure how starlight was spread across different wavelengths, and how spectral lines shifted as stars moved toward us or away from us. In other words, it was not only building a geometric map, it was gathering the physical clues needed to make sense of that map. And this is the crucial point. Better distances do not just make prettier diagrams, they change what a galaxy is. The moment you can place stars in 3-dimensional space and track their motions through time, the Milky Way stops being a luminous blur and starts becoming a physical structure. Regions that once seemed connected turn out to be separated by huge distances. Stars that looked unremarkable in 2 dimensions begin to reveal themselves as members of streams, clusters, or ancient debris fields. Motion becomes biography. There is something almost philosophical about that shift. For centuries we treated the sky as though it were fundamentally flat, because that is how it presents itself to human sight. Even when we knew intellectually that the stars must be scattered through space, the practical experience of stargazing encouraged a kind of illusion. Constellations look like coherent patterns. The Milky Way looks like a band. The sky feels like a dome. Gaia helped break that illusion at scale. It made the dome collapse into depth. And once depth appears, so does chronology, because the longer a mission like Gaia runs, the more precise its parallax becomes, and the more clearly proper motion separates itself from observational noise. Time is not just helping with distance in some abstract sense. Time is sharpening the entire structure of the galaxy. The first data release gives you one kind of picture. The second gives you a better one. The third adds still more depth, still more motion, still more confidence. A map built from years is different in kind, not just degree, from a map built from moments. That is why Gaia's legacy extends beyond the spacecraft itself. Science observations ended in January 2025, and the spacecraft was later retired after its long work at the second Lagrange point. But the mission is not truly over, because the most important part of Gaia was never the metal and circuitry drifting in space. It was the archive. Astronomers are still processing and refining that torrent of measurements, and major releases remain ahead. The machine has gone quiet, but the map it made is still unfolding. This is one of the strange things about modern astronomy. Sometimes the discovery does not happen when the telescope looks. It happens later, when years of measurements are combined and patterns begin to emerge from what once seemed like noise. A mission can end and still continue becoming more important. In Gaia's case, that importance reaches far beyond the Milky Way's broad outline. The same measurements that improve our sense of galactic structure also help identify binary stars, refine the motions of asteroids, reveal distant quasars, and expose objects whose behaviour would have gone unnoticed in a less patient survey. But for our story, the most important gift Gaia gave us was not just precision. It was movement with context. Once astronomers had enough stars placed in 3 dimensions, with enough confidence in their velocities, the Milky Way became something they could begin to model as a whole. Not perfectly, of course. No model ever captures every detail. But for the first time, the galaxy could be reconstructed with a degree of realism that made older assumptions look fragile. Its outer regions were not smooth. Its edges looked disturbed. Its structure seemed to carry the signs of past encounters. And that is where the narrative changes. Up to this point, the challenge has been largely technical. How do you measure distance from inside a crowded galaxy? How do you separate the motion of Earth from the motion of stars? How do you use repeated observation to convert a flat sky into a 3-dimensional map? But once those questions begin to yield, a more unsettling one appears in their place. What if the Milky Way is difficult to understand not only because we are inside it, but because it has not lived a quiet life? Imagine what it means to wind a galaxy backward. Not with perfect certainty, and not like rewinding a film frame by frame, but with enough data to infer how groups of stars must have moved in the past. You begin to see that the present arrangement is not merely a design, it is the aftermath of processes. A galaxy is not a shape, it is an accumulation of events. The more accurately you can track stars, the more the Milky Way begins to resemble an archaeological site rather than a static object. That is why one of Gaia's most important discoveries did not look dramatic at first. It looked like a discrepancy in stellar motion. A few stars were not moving with the rest. Then a few more. Eventually, tens of thousands began to stand apart. They were not following the broad rotational flow of the galaxy in the way the sun does. Their colours and brightnesses suggested a different story. Their trajectories hinted at a shared past. And suddenly, the problem was no longer just how to map the Milky Way. It was how to explain the presence of so many stars that seemed, in a very real sense, to be going the wrong way. You begin by asking whether those stars are really going the wrong way at all. That may sound like a strange question, but it matters because motion in astronomy is rarely judged in isolation. A star is not odd simply because it moves. All stars move. What matters is whether it moves in a way that fits the broader pattern of the system it belongs to. In the Milky Way, most stars in the disk, including the Sun, follow the general rotational flow of the galaxy. They are not marching in lockstep, but they are broadly participating in the same circulation. So when astronomers started to examine Gaia's data in detail, what stood out was not motion by itself, but a population of stars whose motion did not fit that shared rhythm. In one influential analysis of Gaia's second major data release, researchers looked at millions of stars and found roughly 30,000 whose behaviour was distinctly unusual. These stars were moving against the main rotational trend of the Milky Way. They did not look like a random scattering of misfits, they looked related. That is the point where a map becomes a story. If all Gaia had produced were positions and distances, the Milky Way would already have come into sharper focus. But once positions were combined with velocities and basic stellar properties such as brightness and colour, the stars began to sort themselves into families and outsiders. The strange stars did not just move differently, they also showed patterns in their physical character that hinted at a shared origin. It was as though a crowd in a great city had suddenly revealed a cluster of people speaking the same unfamiliar language. What followed was not a moment of magical certainty. Astronomers did what they always do when confronted by something suggestive but incomplete. They modelled, they tested, they asked what kind of past event could leave behind exactly this kind of present signature. And one explanation rose above the rest. The Milky Way, they concluded, had likely collided long ago with a much smaller galaxy and absorbed it. That is an extraordinary thing to say out loud, but it becomes less extraordinary the longer you sit with it. Galaxies are not solitary islands suspended forever in perfect isolation. They live in an expanding universe, yes, but they also live within gravitational neighbourhoods. Small galaxies fall toward larger ones. Tidal forces stretch them, unbind them, and scatter their stars. Over time, the smaller system is erased as an independent object, but not completely. It lingers as structure in motion, as stellar debris, as a population that still remembers a different orbit. In this case, the proposed intruder came to be known as Gaia Enceladus, sometimes given a second nickname that reflected the elongated distribution of its stellar remnants. The collision appears to have taken place somewhere around 8 to 11 billion years ago, when the Milky Way was much younger and the universe itself was still in a more crowded and violent stage of its history. Imagine what that means. Long before the Sun existed, long before Earth formed, long before any living thing looked up at a night sky, the galaxy we now inhabit may already have been reshaped by an ancient act of consumption. There is a tendency to picture such events in overly cinematic terms, as if one galaxy simply slams into another and chaos erupts in an instant. The reality is slower and in some ways stranger. Because galaxies are mostly empty space, stars rarely collide directly. What collides are gravitational systems. The smaller galaxy falls in, its structure begins to unravel, its stars are pulled into new orbits, and over long spans of time, what was once a distinct object is dispersed across the larger host. The violence is real, but it is written in trajectories rather than explosions. And yet the consequences can be profound. A merger does not merely add more stars to a galaxy. It can heat stellar populations, thicken disks, disturb outer structure, and help drive changes in the central regions. One possibility raised by this ancient collision is that it contributed to one of the Milky Way's most recognizable features, the bar-like structure that crosses its center. Not all spiral galaxies possess such a bar. The Milky Way does. If Gaia Enceladus helped create or strengthen it, then a long-vanished dwarf galaxy may still be visible every time we try to describe the basic shape of our own. That realization changes the emotional tone of the whole subject. Earlier, the Milky Way's uncertainty seemed embarrassing in a way. Why did we not know our own galaxy better? But now another answer appears. Perhaps we did not know it because the object we were trying to know was not the simple, internally settled structure we imagine. The Milky Way is not just hard to see from within, it is historically complicated. It contains the remains of other galaxies. And Gaia Enceladus does not appear to have been the only one. As astronomers kept examining the kinematic and chemical signatures buried in the growing data archive, more hints emerged of other past mergers. Another dwarf system was identified as a likely participant in the Milky Way's history, perhaps even associated with Gaia Enceladus in some earlier pairing. Later studies suggested that the Milky Way may have absorbed not just one small galaxy, but several. Depending on how the evidence is grouped and interpreted, the count of likely consumed companions rises beyond a single dramatic collision into a longer pattern of accretion. This is one of the most important conceptual shifts in modern galactic astronomy. We used to talk about galaxies as if they were primarily things that formed once and then slowly evolved in relative solitude. There was some truth in that, of course, but only some. The newer picture is more ecological. A large galaxy grows partly by internal processes such as star formation and gas dynamics, but also by acquiring smaller systems. Its history is not just the story of what happened inside it, it is also the story of what fell into it. That makes the Milky Way less like a pristine architectural object, and more like an old city built on layers of conquest, migration, and reconstruction. Stand in its present, and you are standing on accumulated history. Some stars were born in the galaxy's original disk, some formed in its bulge, some belong to clusters. Some may once have belonged to entirely different galaxies that no longer exist as separate entities. The Milky Way is one galaxy now, but that oneness was assembled, and the assembly is not finished. One of the nearest and most famous examples of this continuing process is the Sagittarius dwarf galaxy. Unlike Gaia Enceladus, which survives mostly as ancient evidence in stellar motion and distribution, Sagittarius is still recognizably interacting with the Milky Way. It has already passed through our galaxy multiple times over the last few billion years, and each passage has stripped away more of its stars. Those stars do not vanish. They are drawn out into streams and gradually added to the Milky Way's halo and outer structure. There is something haunting about that. A galaxy can be in the process of dying for billions of years. It can survive repeated encounters, each one taking more from it, each one weakening its identity, until eventually its stars are no longer easy to distinguish from those of the larger galaxy that consumed it. If you could watch long enough, you would see the word galaxy itself become ambiguous. At what point is a smaller system no longer a separate galaxy, but simply another ingredient in the Milky Way? Sagittarius forces us to ask that question not as abstract philosophy, but as ongoing astrophysics. It has collided with the Milky Way several times already, and is expected to continue its disruption. Some researchers have even suggested that these passages may have stirred the gas of the larger galaxy strongly enough to influence later waves of star formation. In the broadest sense, such interactions may help set the conditions under which new stars and eventually planetary systems emerge. That does not mean the Sun can be reduced to the consequence of one passing dwarf galaxy, but it does mean the Milky Way's environment was probably less serene than older pictures implied. This is where the phrase, "how many galaxies are in the Milky Way?" stops sounding like a clever provocation and starts sounding like a genuine scientific insight. The answer is not literally a large, visible collection of intact galaxies nested inside our own. It is subtler than that. The Milky Way is one galaxy, in the present tense, but in its stars there may be traces of several past ones. It is a single system built partly from many. And once you accept that, much else begins to look different. Those wobbly edges in reconstructions of the Milky Way are no longer just aesthetic curiosities. They are signs of disturbance. The halo becomes not just a spherical cloud of old stars, but a possible archive of past mergers. Odd stellar populations become less like errors and more like evidence. Even the question of galactic identity changes. A galaxy is not merely the stars that formed inside one gravitational container. It is whatever that container has managed to gather and keep over cosmic time. This is, in a sense, why we misunderstood galaxies for so long. We looked for simple shape before we understood process. We wanted a clean diagram before we appreciated assembly. We assumed that to know a galaxy was to trace its outline, count its stars, and classify its visible form. But galaxies are historical systems. Their true structure is inseparable from what has happened to them. If you ignore mergers, accretion, stripping, and disturbance, you are not just missing colourful details, you are missing the grammar of their evolution. At the same time, this new picture solves one problem only by opening another. If the Milky Way has been built and reshaped through repeated interactions, then what exactly are we looking at when we talk about its familiar spiral form? Are those arms stable structures? Are they ancient? Do they rotate as visible objects? Or are they something more elusive, more pattern than substance? Once you have accepted that the galaxy carries scars, you are forced to confront an even more basic visual misunderstanding, because the great pinwheel image of a spiral galaxy turns out to be deceptive in its own way. The stars in the arms are moving, the gas is moving, the galaxy is rotating. And yet the spiral pattern does not behave like the spinning blades of a wheel, which means that even when we finally begin to understand where the Milky Way came from, we still have to ask how a galaxy like this can hold its shape at all. It holds its shape by not holding its stars in place. That sounds paradoxical at first, because when we look at a spiral galaxy in a photograph, the natural instinct is to imagine something like a celestial pinwheel. We see bright arms sweeping outward from a central bulge, and the mind immediately supplies a simple image of rotation. Perhaps the whole galaxy turns as one great object, with the arms behaving like rigid features carried around by that spin. It feels intuitive. It is also wrong. The first thing to remember is that a galaxy is not a solid body. It is an immense gravitational system made of stars, gas, dust, dark matter, and emptiness. Each star follows its own orbit around the galactic centre, and although many stars in a spiral galaxy are moving in broadly the same direction, they are not welded into some giant rotating plate. A spiral galaxy is closer to a crowd moving through a city than to a toy wheel spinning on a table. Once you see that, another problem appears immediately. If the spiral arms were simply fixed streams of stars being carried around by orbital motion, then the inner parts of a galaxy would generally circle faster than the outer parts. Over time, the arms would wind tighter and tighter, twisting themselves into thinner and more wrapped spirals. This is sometimes called the winding problem, and the reason it matters so much is brutally simple. We do not see galaxies whose spiral arms have all wound themselves into impossibly tight coils. Whatever the arms are, they cannot just be permanent lanes of the same stars rotating like painted stripes. So what are they? The leading idea is that spiral arms are better understood as density waves, regions where stars and gas become temporarily crowded as they orbit through the galaxy. The pattern itself can persist even while the individual material inside it changes. In that sense, a spiral arm is less like a row of fixed lights and more like a traffic jam moving through a highway system. The cars entering the jam are not the same cars that leave it, but the jam remains recognizable as a pattern. That picture solves several problems at once. It explains why the spiral form can survive without winding itself into ruin. It explains why the arms can look stable on human timescales, even though the stars inside them keep moving. And perhaps most importantly, it explains why the arms are such visually intense places. When gas and dust pass into these denser regions, they can be compressed. And when giant clouds of gas are compressed, stars begin to form. This is why the arms of spiral galaxies shine the way they do. They are not bright only because there are many stars in them. They are bright because some of the most luminous stars in the galaxy tend to be born there. Massive young stars burn hot and blue, and they do not live long. By the time many of them drift away from the denser regions in which they formed, their lives are already nearing an end. So the spiral arms become lined with fresh stellar light, as though the galaxy is tracing its own active regions in luminous ink. Once you understand that, the visual beauty of a spiral galaxy starts to look less decorative and more diagnostic. Those glowing arms are telling you where gas is gathering, where star formation is active, and where the structure of the galaxy is being refreshed. The arms are not merely ornament, they are process made visible. There are still open questions, of course, because no powerful idea in astronomy arrives without complications. Density waves are the leading explanation, but they may not be acting alone. Some researchers have argued that shock waves produced by stellar winds and supernova explosions can also help shape the spiral pattern, especially by compressing gas and reinforcing zones of star formation. These ideas are not necessarily rivals in the absolute sense. It may be that galaxies use more than one mechanism at once, with self-gravity, orbital crowding, turbulence, feedback from stars, and outside perturbations all contributing to the final structure we observe. In fact, outside perturbations may be especially important. Remember the mergers we just followed through Gaia's motion data? A spiral galaxy is not evolving in perfect isolation. A passing dwarf galaxy, an old collision, or the tidal pull of a nearby companion can disturb or amplify the internal pattern of a disk. The arms we see may therefore be shaped not only by the galaxy's own mass distribution, but by the long memory of past encounters. In that sense, even the graceful symmetry of a spiral may carry the fingerprint of disturbance. There is a beautiful analogy for this hidden behavior much closer to home. In some parts of Saturn's rings, we see wave-like patterns created by the gravitational influence of small moons embedded within or near the rings. At a glance, some of those structures look almost like concentric growth rings in wood, or permanent ridges frozen into place. But what you are really seeing is a pattern generated by orbiting material under gravitational influence. The shape persists, even though the individual particles continue moving. A galaxy is vastly grander and far more complex, but the comparison helps. Pattern does not require solidity. And that leads us toward another invisible actor in galactic rotation, one that changes not just the appearance of the arms, but the motion of stars across the entire disk. When astronomers measure how quickly stars orbit in galaxies, especially far from the centre, they find something deeply unsettling. The outer stars often move faster than the visible matter alone seems able to explain. If you add up the gravity from the stars, gas and dust we can see, the galaxy's outskirts should not behave quite the way they do. This discrepancy became one of the most famous clues in modern astrophysics. Either our understanding of gravity is incomplete on galactic scales, or galaxies contain large amounts of matter that emit little or no light. The second explanation became the dominant one. Dark matter, whatever its underlying nature may ultimately turn out to be, seems to provide a vast gravitational framework extending beyond the visible galaxy. You do not see it directly. You infer it from what it makes everything else do. That matters here because it means the visible spiral galaxy is not the whole galaxy. The stars and glowing gas that dominate astronomical images are embedded inside a much larger gravitational environment. The Milky Way and other spirals are not just disks of light. They are luminous structures moving inside dark halos. Once again, the image deceives. What looks like the main object is only the bright fraction of the full system. There is also a subtler consequence. If dark matter helps govern the overall orbital behaviour of stars, then spiral structure is developing inside a gravitational setting more complicated than earlier astronomers could easily picture. The disk is not evolving on its own. It is responding to the pull of visible matter, invisible matter, internal self-gravity, and the aftermath of past interactions. The reason galaxies misled us for so long is not simply that we lacked enough photographs. It is that the thing being photographed is a layered, dynamical system, not a simple rotating ornament in the sky. And, as always, there are rule breakers. Most spiral galaxies fit the broad expectation that the trailing pattern of their arms reflects the general dynamics of the disk, but a few systems seem to violate that neat picture. One example is NGC 4622, a galaxy whose outer arms appear to lead rather than trail in the normal way. That was difficult to accept at first, because it offended a deeply ingrained expectation about how spiral structure should behave. Yet the more closely astronomers looked, the more convincing the strange geometry became. If the interpretation is correct, then this odd system may have been disturbed by a merger or other strong interaction in its relatively recent past. Another especially intriguing case is the Black Eye galaxy. There, the inner dust lanes rotate in one sense, while gas in the outer region appears to rotate the opposite way. More striking still, the stars in that same outer region do not seem to share the gas's reversed motion. So here we have a galaxy in which different components are not merely moving at different speeds, but in different directions altogether. That is not the kind of thing you get from a tidy, undisturbed system. It suggests either fresh gas still being fed in from outside, or the remains of a merger with another gas-rich galaxy, whose material never settled into the original pattern. These odd cases are more than curiosities. They are reminders that every elegant theory of spiral structure lives inside a messier universe than the theory alone might suggest. Galaxies are not laboratory disks turning in idealized isolation. They are open systems, fed by inflow, scarred by collisions, stirred by feedback, and embedded in dark gravitational architecture. Their spiral arms can therefore tell us something profound, but not something perfectly simple. There is also a quiet emotional shift that happens once you understand this. The classic image of a spiral galaxy stops looking like a static symbol and starts looking like a temporary arrangement. The arms are not eternal fixtures. They are maintained by flow, refreshed by star formation, and vulnerable to change. A spiral galaxy can therefore lose what makes it look like a spiral galaxy. If its reserves of gas and dust are exhausted, new stars stop forming at the same pace. The bright blue populations fade. The visual definition of the arms weakens. The pattern becomes harder to sustain. That is one reason astronomers distinguish spirals from elliptical galaxies, and also recognise lenticular galaxies as something in between. Spirals are rich in the raw material for star formation and show prominent structure. Ellipticals are dominated by older stars and contain far less of the cold gas and dust needed to keep building new stellar generations. Lenticular galaxies seem to occupy a middle ground, with a disk-like appearance but a more faded and ghostly character, as though the galaxy is caught between one visual identity and another. This matters because it means that even the forms we use to classify galaxies are not simply types. They are stages, or at least tendencies, within long evolutionary histories. A spiral arm is not just an arm, it is a sign that the galaxy still possesses the conditions needed to keep that pattern vivid. When those conditions change, the appearance changes too. A galaxy can age out of its own beauty. And now a deeper pattern starts to emerge. First we discovered that the Milky Way was hard to map because we live inside it. Then we discovered that its motion carried evidence of old mergers. Now we find that even the most familiar image of a spiral galaxy depends on pattern, flow, and hidden mass rather than rigid structure. Each step strips away another layer of naive certainty. The galaxy becomes more understandable, but also less simple. Which brings us back to our own. Because if visible light can mislead us about how spiral arms work, and if the disk itself can conceal the history of mergers and the influence of dark matter, then we should be very cautious about assuming that the Milky Way has already shown us everything it contains. In fact, some of the most important parts of our galaxy remained hidden not because they were distant, but because they lay behind the dust of the galactic plane itself, waiting for another way of seeing. Infrared gave us exactly that. If visible light struggles through the crowded, dusty plane of the Milky Way, then one obvious response is to stop insisting on visible light alone. Dust that blocks or scatters ordinary starlight is often far less effective at hiding longer wavelengths. So the same region of sky that can look choked and opaque in visible observations can begin to open when viewed in the infrared. It is not that the dust vanishes, it is that our way of looking changes, and with it, the galaxy changes too. A wall becomes a veil, a blank region becomes a population. What looked like absence turns out to be concealment. That shift has been one of the great revelations of modern Milky Way astronomy. From our position inside the disk, dust is one of the main reasons the galaxy feels so stubbornly incomplete. It fills the central plane, threads through star-forming regions, and blurs our view of the deeper structure beyond. For a long time, this left the inner Milky Way in an almost contradictory state. It was clearly one of the most important regions in the galaxy, and yet some of its most important features remained hidden from us. We knew the centre mattered, we just could not see it cleanly enough to say exactly how. The European Southern Observatory's Visible and Infrared Survey Telescope for Astronomy, better known as VISTA, helped change that. Working from Chile and designed to map large areas of the sky, VISTA was built to look where visible surveys struggle most. Its great achievement was not simply to take beautiful infrared images, though it certainly did that. Its achievement was to turn the obscured inner Milky Way into a region that could be studied systematically, rather than admired from a distance as an astronomical inconvenience. This culminated in a vast infrared survey built across many years of observation. By the time the project reached its major public release in 2024, it had gathered around 200,000 images and generated about 500 terabytes of data. It covered a huge sweep of the inner galaxy, including much of the bulge and central plane, and catalogued roughly 1.5 billion objects. Numbers like that can blur together if you let them. What matters is what they represent. A region that had long been treated as partially hidden was suddenly crowded with detail. One of the simplest ways to grasp the difference is to compare the same nebula in visible and infrared light. In visible wavelengths, a glowing cloud can dominate the scene, beautiful but opaque, with dark dust lanes interrupting whatever lies behind. In infrared, much of that obstruction softens. The cloud no longer feels like a painted backdrop. It becomes semi-transparent, and behind it appears a dense field of stars that visible light was failing to deliver. A scene that once looked like a single object becomes a layered depth of stellar populations. That is exactly the kind of change that matters for the Milky Way. We did not need only more stars. We needed stars in the right places, stars previously hidden in the right regions, stars that could act as markers of structure, and VISTA began to provide them. In one case, looking through the Trifid Nebula revealed objects lying far beyond it, on the far side of the galaxy that had gone unseen before. Among them were Cepheid variable stars, a class of stars whose changing brightness can be used to infer their true luminosity and therefore their distance. Cepheids are among astronomy's most useful distance indicators because their pulsation period is linked to how intrinsically bright they are. If you know how their light varies, you can estimate how much light they are truly producing. Then you compare that with how bright they appear from Earth, and the gap between the two tells you how far away they must be. This makes them far more than just interesting stars. They are measuring tools, cosmic yardsticks planted inside the galaxy itself. Hidden Cepheids therefore mean hidden geometry. That alone would have made the survey important, but the deeper surprise came closer to the galactic centre. Astronomers examining candidate variable stars in the bulge found that not all of them belonged to ancient populations, as older pictures of the central Milky Way might have led one to expect. Among hundreds of candidates, a smaller set turned out to be classical Cepheids, a younger class of stars. Their ages were strikingly low by galactic standards, some only a few tens of millions of years old. In a region long associated mainly with elderly stars, that was a serious disruption to the old story. And when those young Cepheids were mapped, they traced something even more revealing. Buried behind the dust was a thin disk of young stars stretching across the bulge, a structure that previous surveys had failed to uncover. This was not just another hidden cluster or a local curiosity. It was evidence that the inner Milky Way was more dynamically mixed in age than many astronomers had assumed. The bulge was not simply an ancient fossil sitting in the centre of the galaxy, while all youthful structure belonged elsewhere. Younger star formation had been taking place through the midplane more recently than expected. This matters because it changes the feel of the galaxy's history. Earlier we saw that the Milky Way has been shaped by mergers and long-term interactions. Now the infrared view adds another layer. The central regions are not merely old and violent, they are also internally active and structurally complex. Ancient stars are there, certainly, but not only ancient stars. The centre begins to look less like a relic and more like a crowded crossroads of timescales, where very old populations and much younger structures coexist inside the same broad region. Vista also reached toward the Milky Way's deeper past through a different kind of variable star, the RR Lyrae stars. These are ancient objects, commonly associated with old stellar populations such as globular clusters. Their presence in the central Milky Way was therefore especially interesting. When astronomers identified a small population of RR Lyrae stars close to the galaxy's heart, the discovery suggested that some of the innermost regions may preserve the remnants of extremely old systems. In effect, the centre of the Milky Way began to look not just obscured, but archaeologically rich. That fed directly into a long-running question about how galactic bulges form. Do they arise mainly through gas gradually funneling inward and forming stars over time, or through more violent early assembly, including the mergers of smaller systems and ancient clusters? The RR Lyrae population did not settle the question once and for all, but it added weight to the idea that the Milky Way's inner bulge preserves a memory of early hierarchical growth. Once again, the pattern repeated. The galaxy was not yielding a neat, singular origin story. It was revealing a layered one. Then there were the clusters themselves. Infrared observations uncovered previously hidden globular clusters in the crowded inner galaxy, including faint systems near the centre that visible surveys had struggled to isolate. For a galaxy with a relatively modest known population of globular clusters, even a small increase matters. These are not decorative additions to a catalogue. Globular clusters are ancient stellar systems, dense and long-lived, and they tell us about the early conditions under which the galaxy assembled. Finding more of them, especially in dusty regions where they had been missed, means recovering lost pages from the Milky Way's oldest chapters. One of the intriguing possibilities raised by these discoveries was that some of these globular clusters might not merely coexist by chance, but could represent a bound or once-bound pair. That remains uncertain, and caution is essential here, but even the possibility is suggestive. A binary globular cluster system inside the Milky Way would offer rare insight into how such clusters interact, merge, and perhaps build more massive systems over time. In other words, hidden objects do not just fill in a missing inventory, they open new dynamical questions. Beyond the globular clusters, the survey also revealed large numbers of open clusters and stellar nurseries, previously obscured by dust. These tend to be younger and looser collections of stars, often tied to more recent star formation. Their importance is different from that of ancient globulars, but no less real. Together they show that the infrared Milky Way is not merely a darker version of the visible one with a few extra stars added in. It is a fuller ecosystem. Ancient clusters, young associations, hidden variable stars, and crowded fields all emerge into the same expanded picture. What makes this so powerful is that it resolves one misunderstanding only by creating a deeper and better one. We once thought of the Milky Way's hidden regions as gaps in our data. Infrared surveys show that they are not gaps at all. They are densely inhabited, structurally informative, and historically consequential. The galaxy we thought we knew in visible light was a partial translation. Infrared did not replace that translation, it widened it. The Milky Way became more legible, but it also became more complicated, because what had been hidden was not empty space. It was meaningful structure. That is perhaps the most important lesson of all. Every time astronomy changes wavelength, it changes ontology. New instruments do not just reveal more of the same universe. They reveal that the old universe was incomplete. The visible Milky Way suggested one balance of ages, one picture of the bulge, one census of clusters, one sense of how much was there to know. The infrared Milky Way quietly overturned all of that. Dust had been acting like a sensor, and Vista removed some of the censorship. And once you realize how much the galaxy changes when you stop relying on visible light alone, another thought naturally follows. Hidden stars are one thing, hidden engines are another. Because beyond the Milky Way, in the cores of other galaxies, there exist objects so bright that they outshine entire stellar systems around them. And if changes in wavelength can redraw our picture of our own galaxy, then perhaps some of the strangest and most powerful galactic phenomena have also been misunderstood, not because they were faint, but because we had not yet learned how to read what their light was really saying. In the case of quasars, what the light was saying was almost too strange to believe. When astronomers first surveying the sky in radio wavelengths, they found objects that did not fit comfortably into any familiar category. Some shone intensely in radio emission, yet when observers tried to identify visible counterparts, they found only tiny points of light. They did not look like ordinary galaxies. They did not behave like ordinary stars. They seemed almost absurdly compact for how powerful they were. For a time, they were given a cautious name that reflected the uncertainty more than the explanation. Quasi-stellar radio sources. Star-like things that were not really stars at all. The name was eventually shortened to quasar, which made the objects easier to say, but did not make them easier to understand. In fact, for many years quasars remained among the most disorienting objects in astronomy. If they were truly as distant as their spectra suggested, then they had to be unimaginably luminous. A single, small-looking source would have to outshine the combined stellar population of an entire galaxy. That sounded unreasonable, and yet the evidence kept pointing in the same direction. The explanation, when it emerged, did not make the universe feel calmer, it made it feel more extreme. Quasars were not strange stars. They were the bright signatures of supermassive black holes feeding at the centres of galaxies. Black holes themselves emit no light, of course, but matter falling toward one does not simply vanish at once. Before crossing the event horizon, gas can swirl into an accretion disk, heating through friction and compression until it radiates with astonishing intensity. In some cases, powerful jets of ionized matter are launched outward as well, guided by magnetic fields and the rotation of the black hole and its surroundings. A galaxy that might otherwise be seen as a soft blur of starlight can be overwhelmed by the brilliance of its own central engine. This is one of the great observational tricks galaxies play on us. Sometimes they hide behind dust and appear dimmer than they are. Sometimes they do the opposite. Sometimes one small region becomes so bright that it distorts our entire impression of the system. A quasar can make a distant galaxy look less like a galaxy and more like a point source, almost as if the vast stellar city around it had been reduced to a backdrop. The galaxy is still there, but from our perspective its centre steals the scene. That matters because it reveals another way we have misunderstood galaxies for so long. We tend to think observational difficulty comes mainly from faintness, distance, or obscuration. But extreme brightness can mislead too. If one class of galactic core becomes visible across enormous cosmic distances, while quieter galaxies fade from view, then the sample we build is not neutral. It is tilted toward the loudest objects. There is an especially interesting twist here for the Milky Way itself. Our galaxy contains a supermassive black hole at its centre, Sagittarius A star, but it is not currently a quasar. Its accretion flow is thin and faint by comparison, more ember than inferno. In one sense, that is fortunate. A truly active quasar in our own galaxy would flood the surrounding region with far more dangerous high-energy radiation. But in another sense, it means our local experience is misleading. The central black hole of a galaxy does not have to be dramatic at all times. Some are quiet now, but may once have been active. Others blaze only while enough matter continues to fall in. The galactic core is not a permanent spectacle. It is a phase, a state, a feeding condition. That idea becomes even more revealing when it scales downward. For a long time, quasars were associated mainly with supermassive black holes, which made sense because the most famous examples sit in the centres of galaxies and outshine almost everything around them. But it turned out that something quasar-like can happen on smaller scales too. A stellar mass black hole, only a few times the mass of the Sun, can also generate an accretion disk and jets if it has a companion star nearby feeding it material. The result is not a full quasar in the galactic core sense, but a microquasar, a smaller local analogue that can be studied in much greater detail. This was one of the most important conceptual bridges in high-energy astrophysics, because it suggested that the underlying machinery may be similar across wildly different scales. Black holes of very different masses can still launch jets, accelerate particles, and convert infalling matter into intense radiation. The difference is one of scale and power, not of fundamental process. And that means the Milky Way, even without a blazing quasar at its centre, may still contain smaller laboratories for quasar-like physics. One of the most famous is SS433. At first glance, the name sounds dry and catalogue-like, as though it ought to belong to a forgettable point of light. In reality, it is one of the most fascinating jet-producing systems in the galaxy. SS433 consists of a stellar mass black hole in a binary system with a giant companion star. As the black hole pulls matter away from that star, an accretion flow forms, and from that flow emerge jets. Those jets do not happen to be aimed straight at us, which is helpful. If they were, the system would look different and be harder to interpret in the same way. Instead, we get to observe the structure from the side, tracing how the jets propagate outward through surrounding space. What makes SS433 especially useful is that it appears to show more than one jet scale at once. There are inner jets close to the black hole, but there are also larger outer structures much farther away, extending over enormous distances by stellar standards. For years, astronomers have tried to understand not just that these jets exist, but what they are made of, how they are energized, and why their radiation behaves the way it does. This is where the story becomes less about naming exotic objects and more about reading physical processes out of light. The outer jets of SS433 emit gamma rays, and that alone tells you something unusual is happening. Gamma rays represent some of the highest energy light in the universe. They are not the natural glow of ordinary stellar surfaces. Something inside the jets must be boosting particles or photons to remarkable energies. One leading explanation is inverse Compton scattering. In that process, high-energy electrons collide with lower-energy photons and transfer energy to them, effectively kicking them upward into the gamma-ray regime. If that interpretation is correct, then the gamma rays are not just a byproduct, they are a diagnostic. By measuring the energies of the emitted photons and where they are coming from along the jets, astronomers can infer how energetic the electrons must be and how that energy changes with distance. In SS433, the highest energy gamma rays appear to come from nearer the base of the outer jet structures, while lower energy gamma rays come from farther along. That pattern strongly suggests that the electrons begin with greater energy and then lose some of it as they travel outward, partly through interactions that transfer energy to passing photons. But where did those electrons become so energetic in the first place? One possibility is that a shock front near the base of the outer jets acts like a cosmic accelerator. As particles scatter back and forth across the shock, guided and redirected by magnetic fields, they can gain energy repeatedly. The process is often described as diffusive shock acceleration. It is a beautiful phrase because it sounds both technical and strangely intuitive. The particles do not receive one single dramatic shove. They gain energy through repeated encounters, each crossing adding more speed, more momentum, more capability to create the extreme radiation we later observe. What makes this so important is not only the physics of one binary system in our galaxy, it is the scaling lesson. If microquasars can teach us how jets accelerate particles and radiate across large distances, then they become nearby analogues for much more powerful quasar systems in distant galaxies. They are not perfect copies, of course. Scale matters. Environment matters. Black hole mass matters. But the shared mechanisms make them precious. In a field where the most spectacular objects are often impossibly far away, a smaller, local cousin can become an interpretive gift. And that brings us back to a deeper puzzle. Some of the most massive black holes we know of appear in very distant galaxies, which means we are seeing them as they existed when the universe was much younger. At first glance, this feels backwards. Should not older, nearby galaxies have had more time to grow the largest black holes? Should not the longest-lived systems host the most extreme giants? Yet objects like TON 618 seem to suggest otherwise. This black hole, inferred through its quasar activity, is staggeringly massive, and yet the light we see from it began travelling toward us when the universe was much younger than it is now. There are two big reasons this apparent paradox may not be a paradox at all. The first is observational bias. Quasars are among the brightest objects in the cosmos. That means they can be seen from extraordinary distances. A huge black hole in a galaxy that is actively feeding becomes easy to notice compared with a similarly huge black hole in a quieter galaxy whose core is dim. This is one expression of what astronomers call Malmquist bias. Bright objects are overrepresented in distant samples because the faint ones simply fall below the threshold of detection. So when we look deep into space and see spectacular quasars, we are not necessarily seeing the full distribution of black holes. We are seeing the loudest examples that distance allows us to notice. The second reason is historical. The early universe contained more readily available gas in denser environments. Galaxies interacted more often. Matter was easier to funnel inward under the right conditions. Quasars were therefore more common in the young universe, not because black holes were magically favoured then, but because feeding conditions were. Over time, much of that gas was either turned into stars or otherwise made less available for the kind of sustained, central infall needed to power a quasar. So the modern universe may contain enormous black holes that are simply quieter, harder to detect, and less likely to announce themselves through extreme accretion. This changes the meaning of what we think we know. When we say the largest black holes often seem young, what we may really mean is that the brightest active black holes are easiest to see in the young universe. Once again, galaxies have not just been hard to observe, they have biased the story through what they choose to reveal. Dust hid some of their stars. Their own brightness hid their broader structure. Their active cores skewed our sample. The problem was never just a lack of data, it was a lack of context for the data we had. And once you start thinking that way, galaxies cease to look like static classes of objects and begin to look like evolving conditions. A spiral galaxy rich in gas does not simply differ in shape from an old elliptical one. It differs in fuel, in future, in the kinds of central activity it may host, and in the kinds of stars it can still form. To understand a galaxy properly, you have to ask not only what it looks like now, but what stage of life it is in, and what kind of past could have brought it there. A galaxy's shape, then, is not just a visual category. It is a clue. When astronomers look at galaxies across the universe, one of the first things they notice is that form and behaviour often travel together. A galaxy rich in cold gas and dust tends to look different from one that has already used much of that material up. A galaxy flooded with new star formation gives off different visual signals from one dominated by older, redder stars. So morphology, the visible shape of a galaxy, is not merely a convenience for classification, it is often the outward expression of deeper physical conditions, a kind of compressed biography written in light. This is part of why Hubble's long record of galaxy imaging has been so valuable. Over time, it has shown us not only that galaxies come in many forms, but that those forms can be arranged into something like an evolutionary spectrum. Not a strict one-way ladder in every individual case, because real galaxies are messy and environment matters, but still a meaningful progression. Some galaxies look vigorous, dusty, blue and active. Others look pale, smooth and exhausted. Between them lie transitional states that seem to capture the fading of one identity and the emergence of another. Start with the classic spiral galaxy seen face-on. It is one of the most recognisable sights in astronomy. A bright central bulge, arms curling outward through a flat disk, dark dust lanes cutting through the glow, patches of blue stars and red emission marking regions of active star formation. These are galaxies that still possess fuel. They have not yet exhausted the raw material from which new stars can form. In some of them, that process may continue steadily for billions of years, especially if outside influences do not drastically disturb the disk or drive the gas inward too quickly. But not all spirals are equally vigorous. Some are relatively calm. Their arms are still there, their dust still visible, their bright blue stars still present, yet the great red stellar nurseries that signal especially intense star formation are less abundant. In such galaxies, the long work of transformation is happening at a slower pace. They are still living as spirals, still maintaining their broad structure, still building stars, but not with the frantic energy of a system burning through its reserves. Then there are the starburst spirals. These are galaxies that look almost feverish, as though the normal rhythm of star formation has been driven into a higher gear. Their red glowing regions become more pronounced, their blue stellar populations more conspicuous, their disks more visibly alive, with the signatures of recent birth. Something has accelerated the process. Sometimes that trigger may come from internal instability. Sometimes it may come from the pull of a neighbouring galaxy, or from a more direct interaction, where outside gravity compresses clouds and drives them toward collapse. In these galaxies, star formation is not merely continuing, it is surging. That surge matters because it changes the future. A starburst galaxy is not simply more dramatic in the present, it is consuming its own potential more quickly. The same gas and dust that keep spiral arms vivid and supply fresh generations of hot blue stars can be used up on shorter timescales when star formation becomes unusually intense. In a sense, a starburst is both a flowering and a spending spree. It produces beauty, but at a cost. You can see why this matters for the broader question of misunderstanding galaxies. A spiral galaxy is not one fixed thing. It may appear serene from afar, yet internally it can be drifting toward exhaustion or racing toward it. Two spirals can look similar at a glance, while living in very different stages of their histories. One may remain a stable disk for a long time. Another may be heading toward a transitional form because its gas has already begun to thin out, its star formation to slow, its once pronounced structure to soften. This is where the idea of the anemic galaxy becomes useful. Some spirals still retain their broad spiral pattern, but the pattern begins to look drained. The arms remain visible, yet the galaxy has lost much of the bright blue vitality that once sharpened them. Dust lanes weaken. The colour shifts toward a more washed-out white or reddish-white. Only a few stubborn young stars cling to the remnants of active regions. The galaxy looks like a spiral, remembering how to be a spiral. That visual weakening tells you something profound. Spiral arms are not just geometric features floating independently of the stellar population. They depend on ongoing material flow and, to a significant degree, on the presence of gas, dust, and the blue stars that highlight active regions. Once those ingredients diminish, the arms lose their edge. The galaxy can still be disk-like, still rotationally organised, but the familiar pinwheel aesthetic begins to dissolve. It is as if the visible definition of the spiral had depended on youth all along. This fading leads naturally toward lenticular galaxies, one of the most quietly haunting forms in the cosmos. Lenticular galaxies often retain a disk and sometimes traces of bar-like structure, but their spiral arms have largely lost their definition. The dust is far more depleted. Star formation is weak or nearly gone. What remains is a flattened system filled mostly with older stars, often with a ghostly appearance that feels caught between past vitality and future stillness. They look like spirals after the music has faded. There is a special sadness to them, at least from a human visual point of view. In a classic spiral galaxy, you can almost feel motion. In a lenticular galaxy, the motion has not stopped, but the signs of youth have. The blue stars are sparse, the red and white populations dominate. The arms, if they can still be discerned at all, seem more like wisps of memory than active structure. It is difficult not to read them emotionally, even though the underlying physics is simply the long consequence of fuel depletion, orbital evolution, and time. And time is exactly the point. Lenticular galaxies may represent, in many cases, a midway condition between spirals and ellipticals, or at least one major route by which a spiral system can lose its distinctive arm structure and drift toward a more featureless future. They are not necessarily the only path galaxies can take, because collisions, mergers, and environment complicate everything, but they make visible a central truth. A galaxy can survive while the qualities that made it beautiful in one phase slowly disappear. Move farther along that trajectory and you arrive at the elliptical galaxy. Here the contrast with spirals becomes especially clear. Elliptical galaxies are dominated by old stars. They contain far less of the cold gas and dust that sustain star formation in spiral disks. Their stars do not inhabit a neat rotating plane in the same way spiral disk stars do. Instead, they move on a wide range of orbits, giving the whole system a smoother and more rounded appearance. You are no longer looking at a galaxy that advertises internal pattern through arms and dust lanes. You are looking at one whose structure has settled into a broader, quieter form. Quiet, however, does not mean simple. Elliptical galaxies may be among the most evolved visible galactic forms, but their histories can be extremely violent. Many are likely the products of repeated mergers, interactions, and long periods of dynamical reshaping. By the time they appear to us as pale, smooth systems of older stars, the raw chaos that helped build them has already been absorbed into a more stable geometry. Their calm appearance is therefore deceptive in a different way from the deceptive beauty of spirals. A spiral looks simpler than it is because it hides dynamics beneath elegance. An elliptical looks calmer than it is because it hides violence beneath smoothness. There is also something deeply humbling about the timescale involved. In an elliptical galaxy, star formation may have slowed to the point where only a tiny trickle of new stars emerges across vast spans of time. What remains are long-lived stellar populations that will continue burning for billions, even trillions of years. The universe is not yet old enough for us to watch the full final dimming of such systems. We can see late stages of visible galactic evolution, but not the ultimate end. The stars will go on far beyond any human frame of history, gradually aging, fading, and leaving the galaxy ever dimmer. That is one reason the evolutionary picture of galaxies feels so different from the evolution of living organisms. There is no sharp death. There is only the slow loss of fuel, the aging of stars, the fading of structure, and the gradual dominance of old light. A galaxy can become inert in one sense, while remaining visually magnificent in another. It can still contain hundreds of billions of stars, and yet be, by the standards of star formation, almost finished. If you zoom back out, what emerges is a new understanding of galactic life. Spirals, bars, starbursts, lenticulars, ellipticals. These are not just boxes in a catalogue. They are different balances of matter, motion, age, and environment. They are ways galaxies appear when viewed at different moments in much longer histories. A spiral rich in gas still has options. A starburst is spending those options quickly. A lenticular is living on diminished reserves. An elliptical has, in visible terms, largely spent them. And of course, the universe refuses to keep this story tidy. Outside influence can accelerate evolution. Gravitational interactions can compress gas, ignite starbursts, or distort entire disks. A galaxy embedded in a crowded cluster may age differently from one living in relative isolation. Mergers can erase old structure and generate new forms. Gas can be stripped away. Fresh gas can also be acquired. Some systems may linger in transitional phases longer than others. Some may reverse expectations in surprising ways. If the broad evolutionary picture helps us understand galaxies, the peculiar cases remind us not to mistake a useful pattern for a universal script. This is why Hubble's gallery of galaxies feels so rich. It is not merely a collection of pretty shapes. It is a set of frozen moments from many different lives, each one shaped by a mixture of internal process and external influence. A face-on spiral can reveal a galaxy still writing new stars into its disk. A ghostly lenticular can show the remains of a past structure fading into smoothness. An elliptical can present the long afterlife of a system that has, in visible terms, largely spent its youth. The forms differ, but together they reveal that galaxies are not static monuments, they are temporal beings. That thought returns us to the larger mystery we began with. We misunderstood galaxies for so long because we kept meeting them first through appearance. We saw pinwheels, ellipses, bright nuclei, fuzzy smudges, dark dust lanes, and blue clusters. Only gradually did we learn to read those appearances as evidence of process. Shape became motion, colour became age, brightness became selection bias, distortion became memory. The galaxy stopped being a picture and became a history. And once you learn to read galaxies this way, the strangest ones no longer feel like trivial curiosities off to the side. They become some of the most revealing objects of all. Because if ordinary spirals and ellipticals show us the broad grammar of galactic life, the peculiar galaxies show us what happens when that grammar is bent, interrupted, or violently rewritten. They become some of the most revealing objects of all. Because once a galaxy stops behaving the way our neat categories expect, the hidden forces shaping galactic life are suddenly much easier to see. Peculiar galaxies are, in that sense, not side notes. They are confessions. They show us where collisions have torn structure apart, where gravity has stretched disks into tails and rings, where gas has been shocked into new patterns, and where the calm, visual language of spirals and ellipticals gives way to something more honest. The Atlas of Peculiar Galaxies was built around exactly this recognition. Some galaxies do not merely differ in detail, they seem to laugh at the idea that the universe should present itself in orderly forms. At first glance, it is tempting to treat these systems as exotic decorations in the astronomical gallery. One galaxy looks like a ring, another seems to trail a streamer of stars behind it. Another appears to contain incompatible structures sharing the same space. But the longer you look, the more these shapes stop seeming whimsical and start becoming readable. Peculiarity is often just ordinary physics under extraordinary conditions. A collision, a close pass, a tidal encounter, a burst of inflowing gas, a system caught midway through being reshaped. What looks bizarre in still imagery can become perfectly intelligible once you think in terms of process and time. Take a galaxy pair that appears close together on the sky, but shows little obvious sign of mutual disturbance. At first this can feel like a puzzle. If galaxies are really near each other, should they not be pulling and warping one another? Should the encounter not be written into their shapes? But sometimes the answer is not dynamical at all. Sometimes it is perspective again. One galaxy may simply lie in front of another along our line of sight. What looks like intimacy is only alignment. We learned long ago that stars can overlap by chance from Earth's perspective. The same turns out to be true on much larger scales. Even galaxies can mislead us by pretending to interact when they are not truly sharing the same space. And then there are the systems where they definitely are interacting. A ring galaxy is one of the clearest examples. When you see one of these strange structures, it can feel as though a spiral galaxy has somehow been hollowed out, leaving a luminous rim and perhaps a trailing distortion behind it. But a likely explanation is often much more dynamic. A smaller galaxy plunges through a larger disk, and the gravitational shock drives matter inward and then outward again, setting off a propagating wave through the system. The result can be a ring of compressed material and triggered star formation, expanding through the aftermath of the collision. What looks like a bizarre geometric symbol is really the visible echo of an impact. That is the lesson peculiar galaxies keep teaching. A strange shape is often frozen motion. A streamer of stars is tidal stripping made visible. A warped arm is a memory of gravitational harassment. A compact, dense remnant may be what survives when a larger structure has been stripped down by interaction. If normal galaxies teach us the broad rules of galactic life, peculiar galaxies teach us how those rules are bent by environment and encounter. They are the places where the hidden verbs of galactic evolution become impossible to ignore. There is even something clarifying about the emotional effect they produce. Spirals often invite admiration. Ellipticals often invite a kind of serene respect. Peculiar galaxies provoke curiosity almost immediately because they make no attempt to look stable. Their forms are too obviously in flux, too clearly troubled, too uninterested in symmetry. They force the viewer to ask, what happened here? And that question is exactly the right one. Not what type is this? Not where should this fit in the catalogue? But what happened here? In that shift from type to event, we come much closer to understanding what galaxies truly are. Some of the strangest known systems also remind us that not every galaxy is grand in scale. There are dense, compact galaxies that seem almost implausible in how much stellar matter they contain in such small volumes. These are not merely miniature versions of larger galaxies. They may be remnants, stripped cores, survivors of more massive structures that lost much of their outer material through interaction. Once again, what looks like a tidy object in the present may actually be the final hardened center of a much more extended past. Galaxies can shrink in apparent dignity and still preserve evidence of what they once were. All of this reinforces something we have touched again and again throughout this story. Misunderstanding galaxies was never just about not having enough images. It was about taking appearance too literally. We looked at spirals and saw permanent arms. We looked at the Milky Way and assumed our home system should be simple to know. We looked at quasars and struggled to believe what their brightness implied. We looked at the visible sky and forgot how much dust and wavelength bias were editing the scene. Peculiar galaxies are the most dramatic rebuke to that habit, because they show so openly that form is history under tension. And then, just when galaxies seem to become most unruly, they acquire one more role altogether. They become instruments. This happens on the scale of galaxy clusters, where gravity itself begins to change what can be seen behind them. A sufficiently massive cluster can bend the paths of light from more distant galaxies, stretching those background systems into arcs, duplicating them, magnifying them, and making them visible when otherwise they might have remained too faint or too small for us to detect. The effect is called gravitational lensing, and it is one of the most beautiful examples of the universe turning matter into optics. A cluster does not merely occupy space, it curves space-time strongly enough to function as a natural telescope. That idea would have sounded almost fantastical before general relativity gave us the language to describe it. Yet once you see the images, the logic becomes hard to escape. Long luminous arcs curve around a foreground cluster. A distant galaxy appears more than once because light from it has reached us along different bent paths. What ought to have remained hidden becomes visible through the gravity of something nearer. A galaxy cluster becomes a magnifying glass millions of light years wide. This matters for more than visual wonder. It means the universe helps us study itself. Some of the most distant galaxies known have been glimpsed because lensing stretched and amplified their light. We see them not only as they were billions of years ago, but as they were when the universe itself was still relatively young. A galaxy cluster in the foreground becomes a bridge to a time when galaxies were only beginning to assemble into the forms we now know so well. The further we look, the younger the universe becomes. Lensing therefore turns the warped present of one structure into a window onto the deep past of another. Notice how fitting that is for the story we have been following. We began with the problem of being trapped inside our own galaxy and trying to infer its shape from within. We moved through parallax, motion, mergers, density waves, infrared surveys, black hole engines, and the visible life stages of galaxies. Now, at the end, galaxies do something almost poetic. They stop being only the objects of observation and become part of the observing apparatus itself. Their mass bends light. Their history alters what we can know. Their very existence changes the visibility of more distant realms. That is a wonderful final correction to our old misunderstanding. We once imagined galaxies mainly as isolated shapes to be classified, but the fuller picture is far richer. A galaxy is a place where stars are born and die, yes. It is a gravitational structure, yes. It is a host for black holes, clusters, dust, gas, and perhaps planets and life. but it is also a participant in a larger cosmic network of influence. It feeds on smaller systems. It is fed by inflow. It distorts space-time. It shapes what nearby galaxies become. It determines what can be seen behind it. To understand a galaxy is therefore never just to understand one thing. It is to understand relationships. And perhaps that is the deepest answer to the question we started with. We misunderstood galaxies for so long because we expected them to be simpler than they are. We treated them as pictures before we learned to read them as histories. We assumed our own galaxy should be easiest to know, when in fact, living inside it makes perspective, distance, and structure harder to disentangle. We trusted visible light too much and underestimated what dust could hide. We underestimated how much mergers shape galactic identity. We mistook spiral arms for solid forms, bright quasars for easier truths, and classification for explanation. In each case, the universe did not really deceive us. It simply refused to become legible until our methods matured. And once they did, the reward was not a smaller mystery. It was a better one. The Milky Way is now more intelligible than it was a generation ago, but also more layered. We can see it as a cannibal galaxy, a structure built partly from absorbed companions. We can trace stars in 3 dimensions and uncover the motions that preserve ancient collisions. We can use infrared light to look through the dust and recover hidden populations near the centre. We can understand spiral arms not as rigid shapes, but as patterns sustained by flow, gravity, and star formation. We can interpret quasars and microquasars as black hole engines acting across scales. We can place spirals, lenticulars, and ellipticals within broader evolutionary pathways. And we can read peculiar galaxies and gravitational lenses as demonstrations that disturbance and curvature are as central to the universe as order and symmetry. In other words, galaxies became harder in one sense, just as they became clearer in another. The more we learned, the less any galaxy could be reduced to a simple image. A spiral is not just a spiral. An elliptical is not just an old, smooth glow. A peculiar system is not merely a cosmic oddity. The image is always a clue to something deeper. What we call misunderstanding was often the interval between seeing and interpreting. There is also a more human lesson in all of this. We are creatures who evolved under one small sky, on one small world, with senses tuned to local scales. And yet we have managed, through patience and instruments and mathematics, to infer the structure and history of systems so vast that even their nearest stars are almost incomprehensibly distant. That achievement is easy to take for granted because it arrives to us finished, turned into labelled images and polished diagrams. But behind each one lies a struggle against perspective, bias, hidden matter, missing wavelengths, and the sheer mismatch between human intuition and cosmic reality. Maybe that is why galaxies feel so compelling. They are not just beautiful, they are resistant. They force us to grow intellectually in order to see them properly. They refuse to be known all at once. Every improvement in our understanding seems to come from first recognizing that some earlier picture was too flat, too literal, too comfortable. And that process is probably not finished. Future surveys, new missions, better infrared maps, more precise motion catalogues, and deeper observations of the early universe will change the story again. The galaxy you think you know may still turn out to be a partial draft. For now, though, we have a far better answer than we once did. Galaxies were misunderstood not because they are impossible to understand, but because they are dynamic, layered, biased, obscured, and historical all at once. They are among the most intricate structures the universe builds, and it took us a long time to stop treating them as ornaments in the sky and start reading them as living records of cosmic time. If one idea from this stayed with you, I'd love to hear which one. And if you enjoy this kind of subject, you can stay with the channel for more.